Today's topic is electron weak. And we have to discuss a few things, such as which which gauge group we should use to construct the system, spontaneous symmetry breaking, Higgs mechanism, and then the quark mixing, and then something called chip mechanism. This is a way to avoid forever changing neutral current. And then finally there will be a discussion, mention of actual anomaly. Okay? Okay. So let's start with a brief history about the electron weak unification. The Schwinger was probably the first one. This was in 1957. He published a very long paper called Fundamental Interactions. And they combined electric and weak interaction together. And then Grashow in 1958, he gave the same problem to Grashow also. This is his PhD thesis. And then Grashow also published a paper in 1961, and it has SU2 causing more. And more yes. Then Salam and Ward. This is the same word as the word identity you learn in gauge theories. They published a paper in '64. And then Salam himself in 1967 in the conference proceedings. And finally, Weinberg. In this is 1968, 67, okay? And here, he used the SU2 cross U1, and then plus Higgs. Okay? What's interesting is that in this paper, he only discussed the model for leptons, no quarks. And the reason was that he, at the time, did not believe in quarks. So he just, I don't know if you remember, the title of his paper is called A Model for Leptons. Let's start from Fermi's observation. If you compare the proton, and then an electron interaction, electromagnetic interaction with a photon, and then you have gamma mu and gamma mu there. So that's QED. Then the Fermi wrote a theory for beta decays, and he made the following observation. Here's a neutron, become a proton, and then something here, and then turn into an electron and then neutrino. Okay. And what he wrote down here is a gamma mu here, and a gamma mu there. Okay. And he made the following observation. The only difference between this vertex and that vertex, for example, is that there's no charge exchange. The proton stays a proton, but here, neutron turn into a proton, and then electron and then anti-neutrino have different charges. So there's a charge exchange. Okay, so the difference. So this is beta decay. So the difference. One is that charge exchange. In a beta decay. And then the second thing is that here, it turns out everybody, the Fermi interaction is given by this G F square root of 2, and then you have P bar gamma mu neutrons, and then I have neutron gamma mu and then neutrino. Okay, and then the coupling constant GF is order 10 to the minus 5 times GeV minus 2. Okay, so this means that the interaction here is very long, very short ranged. So it's a short range. So if there was a particle, if there were a particle exchange, it have to be very heavy. Okay? So for this low energy process, you don't need to put in a particle exchange here. But if you want to generalize it to higher energy things, you might want to introduce a vector particle here, and this is called intermediate vector particle, vector bosons. And they usually is called IVP. Okay? Now the problem with if you want to introduce a particle which exchange between the two vertices in analogy with this photon exchange, then you have to use spin 1 and with the massive And this particle will have the provocator. G mu minus k mu over m squared and the k squared minus m squared. Now, at the low energy, when the k equal to 0, and that just becomes, this thing becomes G mu equal to m squared. And that led to a theory, okay? So that's low energy. Now at high energy, when k go to infinity, then this go to order 1. Because there are 2 powers of k here, and then there are 2 powers of k there. So this will be very bad at high energy behavior. So if you propose a vector particle exchange between the two here, then this will give you a theory which is not renormalizable. Not renormalizable. Okay. So there are 2 crucial questions. For electroweak unification. One is which group? Okay? And then second is how to give intermediate vector boson a mass and still maintains renormalizability. Okay, so those are the 2 questions. Let's start with the first one. So the simplest possible case is to just look at the leptons as Weinberg did. Like that. So this will be considered as a topic in SU2 or something. And then, because we know that the theory is a V minus A, so let's construct a current like this, neutrino, and then have a gamma lambda, 1 minus gamma phi electrons. So this is to incorporate V minus A. And then we have the electromagnetic current, EM, and that's equal to minus E gamma mu E minus because electron gets a minus charge, negative charge 1. Okay. So let's construct the following object called T plus. This is the generators for some gauge group, for example. Okay, T is 3x, and then a J 0 from here. then the T minus will be just the T plus emission conjugate. And then we have a charge, electric charge, for the minus D3x, and then E bar, gamma 0, E. Okay? Now you can using the canonical commutation relation for electron and neutrino fields, then you can find out that the T plus and the T minus, the commutator, should be equal to T 2T3 if it's SU3 group, and you work it out, and then the T3 equal to 1/4 D3x mu emission conjugate 1 minus gamma 5 mu minus E plus 1 minus gamma 5 E. Okay? And the point to observe is that this is not equal to Q. In other words, these two plus that one don't form a group, because we get this is not equal to Q, so we need something else. So what do? If we want to form a group, then this must be in the generators, or so let's do this. So what are the options? One is to introduce a neutral vector boson which couples to T3. So we introduce another vector. In other words, we have a vector boson here, a vector boson there, and then we need this, so we introduce another one. And then we also need a U1 for the electromagnetic interactions. So when you introduce this become SU2 or this, so this together just form SU2. And this is the Weinberg's choice. Now, alternatively, you can introduce heavy charged electrons. I'm not going to discuss it in detail, except to say that if you do this, then you don't need this neutral vector bosons, so it's to avoid the need for neutral vector boson. Okay, and this was suggestion proposed by Georgia and Garcia.
How does it work? How does it work? This heavy charge electron option. How does it work?
You to make sure that the charged electrons turn out to be equal to this. But in order to do that, you have to introduce other, this will have more current, more contribution from the charged electrons. and then you'll be able to do it in such a way that these things is exactly equal to electromagnetic current. And if you want to know the details, you can read the Chen Li.
Okay.
Okay. But this was very quickly. This was ruled out. Once the neutral weak current was discovered in 1973. Okay, so this we don't have to worry about this. And this is one. Okay. So we can write down the gauge fields. The Lagrangian for the gauge field will be equal to -1/4 of W mu nu A W mu nu A. Okay? And that's the SU2. And then 1/4 B mu nu. This is equal 1. Okay? Oh, I call it G mu nu. G mu nu. G mu nu. Okay. Now this W mu nu has the standard form. D mu W nu A minus D mu W nu A. And then minus G epsilon ABC. This is the totally anti-symmetric tensor. And then you have W mu B, W mu C. And then the G mu is just D mu B mu minus D mu B mu. Now you may wonder why we have to use non-abelian gauge group, and I think there are two reasons. One was because we want to unify the weak induction, the electromagnetic inductions, and we know the photon is abelian gauge field. So if you want to combine them, the other component must also be a gauge field. And the other was more profound. Namely, people realized the only way to give the vector particles a mass and still maintains the theory is still renormalizable. The only way to do that is to use Higgs mechanism for a gauge group. So the two together, you are led to the idea that the only way you can do this is to use non-abelian gauge theory. Okay? So before the symmetry breaking, there are 4 massless gauge bosons. Here we have 3, and here's 1, right? So okay. If we take a first generation, then we have left-handed electrons, electron, and then we have the quark, left-handed quark, say UL, and then DL. And then here, in addition, we have right-handed electrons, and this is a singlet in the SU2. And here we have two of them, UR, right-handed, and the DR. These are all singlets. And we can construct the T plus as before there. We have T3x, neutrino, electron, left-handed, and then plus the quark contribution. And then the T minus will be equal to T plus, emission conjugate, and then you can commute using just T plus T minus equal to 2T3, so T3 becomes 1/2 T3x neutrino, neutrino, and then I have electron dependent, and then plus the quark contribution, plus DL plus DL. Okay. Now we still have not figured out what the quantum number for the U1 here. We know we need a U1, but I have not specified what the quantum numbers will carry. Okay? So we know U1 has something to do with the electric charge. So Q, we know, is equal to T3x, and then have a minus E plus E minus. And then E. And then 2/3 U plus U minus 1/3 D plus D. Okay? And as you can verify very quickly that this is not equal to 0. So we cannot take this to be the U1, because if we want to have an SU2 course U1, that means that these two groups must commute. But this is 0, so this cannot be the, so this Q cannot be the U1. So what could it be? Well, we have to figure out that we have to find a quantum number which commutes with all plus t minus and t3, okay? Now, it turns out that you can find such a quantum number, and such a quantum number is this. Is q minus t3. Okay. So q minus t3 commutes with all the quantum numbers in SU2. So this will be the U1. So this is the U1. And then the convention, it would define something called weak hypercharge. Y is equal to 2q minus t3. Okay? I'll give you an example. For example, we have an electron here. Now, you remember the electron doublet is a neutrino and the electron here. So, for the, let's look at neutrino. 2q equal to 0 and the t3 equal to minus T3 is 1/2, because it's upper half here, so that equal to -1. Now if the electron, that will be equal to T2, and the Q equal to -1, and T3 equal to -1, so it's minus 1/2. Okay, so that's equal to also -1, is that right? Yeah. Now how about the electron singlet? Two Q equal to -1, but T3 equal to 0 because it's a singlet, so it's -0. So it's -2. Anyway, so you can go on and figure out all the quantum numbers here, and then you can just write down the Hamiltonian, or Lagrangian. Let me just write it out for you, okay? For the fermions. Left-handed leptons, gamma mu. And then I have G, 1/2 tau dot W. Mu, that's the SU2 here. And then I have to include this coupling to the U1. And the U1 will be equal to minus G1, 1. A different coupling constant, 1/2 YL. And then P mu. And then I have L left-handed, okay? And the same thing here for the quark left-handed. I'll have tau dot W here, and then minus G prime 1/2. And you have a Y quark, and then P mu Q L. and then I have to plus the right-handed electrons, and in this case, there is no coupling to the SU2 because it's a SU2 singlet. And then I have to add the coupling to the U1. That's I here, right? Yeah. No, I'm sorry. I put the I here, so there's no coupling. I here. I there. And then plus, you see that the coupling is 1/2 Y, and the 1/2 Y here is a -2, so it becomes +1. G1 B mu E R, and then for the right-handed quark, gamma mu, I gamma mu, you can work it out, minus G prime, 2/3 B mu, U R, and then the thumb quark. G 1/3 B mu D R. Okay, and the whole Hamiltonian is equal to L. And here for the gauge field, and then for the fermion. Now, notice the following, that I cannot write down a gauge invariant mass terms. So, no gauge invariant mass term. Okay? Yeah. Well, you know in order to write down a mass term, you must include the left-handed and the right-handed fermions. And we don't have that. Well, first of all, you just say E, you might want to write something like this, but this is 0, right? Because EL equal to 1/2 1 minus gamma 5 E, and this is equal to this. And that is equal to E here 1/2 1 minus gamma 5 gamma 0. And then when I move the gamma 0 through here, that just becomes E star gamma 0. And then here's 1/2 1 plus gamma 5. So that's equal to E bar 1/2 1 plus gamma 5. So when I make this combination, I get there's something here, and then I have 1 plus gamma 5 from here, and then from here I have 1 minus gamma 5, and that equals to 0, okay? And then I cannot write down EL, ER, because it's not gauge invariant. Because this is SU2 doublet, and this is SU2 singlet. So you put the doublet and singlet together, it's not gauge invariant. So there's no gauge invariant mass balance. Okay? And that's very important. That means in order to introduce masses to the fermions, we have to do something else. And that's where we need to introduce the Higgs boson. Oh, I shouldn't use this bulk. So, we have to introduce a complex doublet. Scalar of phi equal to phi plus and the phi 0. So each one is a complex field, so the total is 4 field here, 4 degrees of freedom. Okay? And if we compare this with the what's the weak hybrid charges, then you'll find that for this one is 2 charges plus 1. T3 is minus. T3 is 1/2, so it's minus 1/2. So that's equal to 1. For the lower component, the charge is 0, and T3 is minus 1/2, so it becomes 1/2. So equal to 1. In other words, this while phi, the hybrid charge of phi, is equal to 1. So you can write down the coupling of the Higgs, the scalar field to the gauge field using the instruction we learned from there, okay? So the potential, we anticipate to have a spontaneous symmetry breaking, so we introduce a potential energy of the following. Potential energy. We have something like this. Here's the phi, and then the V, and you have something like this. Okay. Now you should imagine that this is 3-dimensional, actually it's 4-dimensional. This should be a circle like this. And I'm not a very good drawing, but you see what I mean, that you have to make a rotation like this. And the idea of spontaneous symmetry breaking is the following. The potential is clearly asymmetric with respect to rotation in these directions. So it's totally symmetric. But in order to quantize the theory, you have to pick a point. And then once you pick a point, for example here, then you select a particular direction. The symmetry with respect to rotation is now broken. And that's why it's called spontaneous symmetry breaking, okay? Now, if you move a particle around the circle here, near the bottom here, it's like this. This is a circle on a surface, on a plane. So you don't need to put any energy to move from one particle from here to there, because this is all have the same potential energy. That corresponds to 0 mass excitations. And there are 3 of them. But there's another way you can move the particle around here. move here like this. And it looks like it's a harmonic oscillator, so you need to add energy in order to move this around. And that's called massive excitation. And this would be the Higgs. Now we have to deal with these three zero mass excitation, which are called the Goldstone bosons. Okay? We don't want Goldstone boson. We want to have vector particle with mass. So how do we do that? Well, we have to use something called Higgs mechanism. So the next thing is talking about Higgs mechanism. Now, if you pointers using these pointers for polarization, then this field here will have a vacuum expectation value. It will be 0 here, and here is the usually called square root of 2 of V like this. So let me write V square root of 2, 0, 1. And call chi equal to 0, 1. Okay. Then the Lagrangian for the scalar doublet will be equal to d mu phi, like this. And then minus V of phi, and the V of phi is given by this picture like this. Okay. So, okay, write it down for you. So the minus mu square phi square plus lambda phi dagger phi square. So what is the theme? Is the covariant derivative. Or the covariant derivative for the Higgs will be equal to d mu minus Ig 1 half tau for W, and then minus 1 half, or minus I G prime 1 half, and then there's a y, but the y is equal to 1. So I have b mu phi. Okay? And what I want to do is to take this and look at the mass term. Okay? And the mass term will be produced by the vacuum expectation value. So for example, I don't have to include this because the vacuum expectation value is a constant. So the derivative will apply to it, just give me 0. So the mass term will be equal to what? There's I here. There's the mutual conjugate is this, so the I will cancel out. And what I have is G 1 half tau W mu plus G prime 1 half B mu. And then I have chi, and then I have V over 2, square root of 2. I should do this. I'm taking this, so equal to V over square root of 2. And then so I have a chi like this here. And then there's another one here, G minus 1/2 tau over W mu by G prime 1/2 mu. Oh, there's mu should be here. And then I have chi. And then I have another square root of V over 2. So I have square. Then there's a factor 2 here, factor 2 there. So the total will be V squared over 8. And then a chi times G 1/2 tau W plus G prime 1/2 B mu. And then I have a G. Oh, the 1/2 disappears because I already taken out here, right? Anyway, well, G tau over W plus G prime B mu, and then have a G tau W mu by G prime B mu, and then a chi. Okay, so those are the mass terms. I can read them off. So let me do a little algebra for you. I have tau over W from one factor, and then there's another one. So I get this square. And this square is equal to W squared, right? It's a simple algebra. The tau, the Pauli matrices have this property. And then I have tau of W, and then I have B mu like this. Let me suppress the Lorentz index here, just like this, B, and then I have the two of them, right? So two. Now, if I write this out, I have tau plus W minus W plus, and then tau 3, W3. These two terms will not contribute because the chi equal to 0, 1. So this will raise this to become here, but the other side, chi is still this, so they cancel, give me 0, right? For this, I cannot lower it anymore, so I get 0. So the only thing which will contribute is this term. And the tau 3 applied to this give me minus. So this equal to 2 W 3 B. And then the last one is B squared. Okay? And once I've done that, I can remove the chi there, because the scalar point is 1. So, the mass term equal to V squared over 8, and then I get G squared W1 squared plus W2 squared. And then I have let me do here, G squared W3 squared coming from here. And then I have 2 G prime W3P, and then I have the G prime square P squared. Okay. So I can write this as V squared over 8, G squared W1 squared plus W2 squared. And here is G W3 minus G prime B1, P. Now if you call W plus minus equal to the square root of 1/2, W1 minus plus W2 for the charged bosons. And then clearly this is a particular combination which give me one of the massive gauge bosons. So let's call it G field, okay? So Z will be equal to G W3 minus G prime B, but I must normalize it because of this, so I get square root G squared by G prime squared. So then you get, write down the masses. So the mass equal to will be equal to m W squared W plus mu W minus mu, and then plus 1/2 mg squared z mu z mu. Okay? And the masses you can just read off from there. mw squared equal to 1/4 G squared V squared, and the Z mass is 1 over V squared, and here's the G squared by G prime squared. So here's the Higgs mechanism. Here I have 4 degrees of freedom, which include 3 massless goldstone boson plus 1 Higgs. After doing this, the zero mass goldstone boson disappear, and usually it's called eaten up by the massless gauge bosons, and then turn them into massive gauge bosons, because you know that the vector particle, if you get the mass equal to 0, then there are only 2 degrees of freedom. Just like a photon gets 2 transverse polarizations. Then if the mass is not equal to 0, then there are 3 of them. So the 3 massless goldstone bosons originally disappeared and appear as the 3 longitudinally polarized gauge boson with a longitudinal polarization. Okay? So it becomes massive. And that's how you gain masses from the Higgs mechanism. Okay, let's have a break here. Okay, let's continue. Among the list, the topics I listed here, I already talked about this. So the next thing is about quark mixing. I already mentioned that without the Higgs, you cannot write down a mass term for fermions. Now with the introduction of Higgs, we can write down mass term Lagrangian, which will give you the mass. So let's call the leptons, given I. I means generation. This is generation. And the left-handed, this will be equal to neutrino, and then electron. And then this means the EI means electron, muon, and tau. Okay? And then we have the similar thing for quark. I have a UIL, and then I have a DIL, and then UI means a U, charm, and the top. And you have a D, the down quark. This will be S, will be, the down quark, will be strange quark, and the bottom quark. Okay. So we can now write down the Lagrangian, which couple the fermions to the Higgs. Okay. So let's write it down. For example, what do I say? Call Y. I don't know why I call Y. You have, we have a lepton doublet, any one of them, and then this can combine with the Higgs doublet to form this is a doublet and that's a doublet, so they can form a gauge invariant object here, and then we have the right-handed of leptons, so I get right-handed here. And this can be any of the three generations. It doesn't have to be the same generation, so it could be a J here. So I have a coupling constant called F, I, J, and this refer to leptons. And then I have same thing for the quarks, and then I have Q, bar I, L, phi, and then I have U, J, R. Okay? And this will refer to the upper quark, and then again I have J. And then I have to write down another one for the down quark. Oh, no. Phi. This is not quite phi, but it's, oh, this is phi. D, J, R. It's here that I call some phi twiddle. This is a usual isospin doublet and form a scalar. But here, what I have, I twiddle is equal to I times 2 phi. In other words, for a doublet here, Q and phi, you can form two gauging rank combination, one of this and one of that. Now, I'll give you an analogy. In a two-dimensional vectors, if you have two vectors on a plane, it's not very good. What I want to say is that, okay, just do it. If it's in two dimensions, what you can form a scalar is take the scalar product, A to B. So A and B are two-dimensional vectors. But there's another one, the A cross B is also rotational in line. And the reason is that when you rotate the A and B same together, it doesn't change the cross product, A cross B. It's always pointing up, right? You see what I mean? And that's the same thing here. But the details are not important. The important thing is that when I do the vacuum expectation value, 0 and 1, then you will see that the mass term will equal to this, V over 2, and then I have VFL, and then IJ, the same thing here, IL, EJR, and then I have F, a quark, IJ, U, a Q, IL, and then UJR, and then there's another one, B quark, IJ, and Q, IL, and then a DJR. So they look like mass term because they're left-handed, right-handed, left-handed, right-handed. But they are not diagonal. It's I and J, okay? So, so the mass matrix will be equal to Ij like this, equal to minus. A means is here, this or that, okay? So V over square root of 2 F I J. So it's a matrix. A equal to L, U, D, yeah. Okay. So it's a matrix. And you have to diagonalize it in order to get the mass eigenstate. Must be diagonalized to get mass eigenstate. Yeah.
If neutrino is it's not massless, then you probably get a similar term like a Fock sector.
If
neutrino have mass.
Oh,
then,
yeah.
then
right. I assume that the mass of the neutrino is 0. Assume. For the moment, okay? Next week, I will talk about the situation when we remove this assumption. I wrote down the Lagrangian for fermions which couple to the gauge fields. And then when you do this diagonalization, then those gauge eigenstates will be modified by a unitary transformation. And so all the fermions with different flavors will mix. So this diagonalization means that the gauge eigenstate, flavor eigenstate, be mixed. Will be mixed. So you have a U DSE, and then you apply to a unitary transformation to it to get the D prime, S prime, and the B prime. So this is the one which diagonalizes the mass matrix, and therefore all the flavors are now mixed. Okay, and this is this is the CKM matrix. And for details, you have to read the chain and E. I just want to make a point that in order to have CP violation, to have a CP violation phase, we need at least 3 generations. Okay, so 3 generations is the minimum number of generations you need to have CP violating phase. In this case, there's only one phase which violates CP. And for this work, the C, not C, but the KM got the Nobel Prize, right? A few years ago. Kabibo didn't get it. And he was very upset. And I think a year later, he just died. Okay. So, what mixing is done here. The weak neutral current you can write it down like this, W 0. You can find the form for the neutral current in channel E. And basically, you don't have to know everything, just know the fact that UIL, comma mu, UIL, comma I, and each I, this corresponds to C, U, C, top, like that. And also you have C right-handed, and then you have the same similar thing. UIR, comma mu, UIR. And then you have similar D. let me not write down over, just to say this is D, and that's D, dy, left-handed. Okay, let me write down anyway. D. Okay. Now, one can write U to be a column vector U, C, T, and then the D will be equal to D, S, B, and so on. And so, the electron neutral current can be written as this form: U, gamma mu, U. It's a column vector and column vector, and then you have GR, U, U bar, gamma mu, U R, left, and then plus the D quark. The point is that when you apply this unitary transformation to it, all you get is just for example, D bar gamma mu right-handed D L, and then you apply this unitary transformation to it, you get D bar L prime U inverse gamma mu U D L prime. And the U bar U is equal to 1, so this is equal to D prime gamma mu D L prime. Okay, so the idea is that the original here, there are no flavor changes. U to U and D to D, okay. The flavor here and I are the same. And then after the unitary transformation, they still stay the same. So no flavor changing neutral current. After the mix. Okay? And you should realize the following. When this Jim, Russia, I don't, he's Greek. I don't know how to spell his name. Ilion, I don't know. Something like this. And then Miami. Okay. When they proposed the idea, at that time the Chang quark was not discovered, or the B quark was not here. So, unless if a generation is complete, when you do the unitary transformation, this property will not be preserved. I don't know if you, I hope you understand what I'm saying. Unless the, when you apply U to it, unless all three appears, then the unitary transformation will still maintain the fact that the flavor are still diagonal. If one of them is missing, then apply the unitary transformation to it, then it will mix the different flavors. So that's why when Jim paper was published, you only have U, E, that's one, that's good, but only S, and here it doesn't have anything. So they introduced, they claim that you should have another quark here called charm, and then of course later it was discovered. Okay, so that was the original idea of why charm was needed. Okay. Now, let's talk about the actual anomaly of today's last topic.
But at that time, it should be only have 2 generations, right? When they introduced the
Yeah, only have 2 generations. So then the mixing was just between 2 generations. Okay, and then when you discover B and the top, you discover B, then you know you must have T, the top one. Okay, yeah, you're right. So this anomaly, I'm talking about the anomaly here. You have T mu lambda, A, B, C, K1, K2, Q. And this is a type order product of 4 current. You have V mu A X, V mu B Y, or X2. And then A lambda C 0. And then comes the exponential E I K1 X 1 plus I K2 X2. Okay. So you have, yeah, this is the amplitude you have, and then the V mu A is psi r comma mu Ta psi, and then A mu A will be equal to psi or C, okay, comma mu comma 5 Tc psi. And then there's another one I need called pseudo-scalar density psi bar gamma 5 T Z. Okay. B. Psi and Z. I will just be very brief. This vector currents are conserved. But the T A mu say C is not equal to 0. You got 2m PC something like that. This is called naive partial conservation actual current, but actually there's an additional term, and this additional term is called anomaly.
你那个积分 D4x 还是 D4x1 D4x2？
X1 K1 X1
一个积分的变数跟
Oh, yeah. That's what you mean, right? Okay. Now, you take the divergence of this Q lambda T mu nu T ABC, and here's a mu lambda. You get 2m T mu nu T ABC mu nu. This is the one that you replace this by P. Yeah? And in addition, there's a term like this, 2 pi squared epsilon mu nu sigma rho, and then you have K1 sigma K2 rho d sigma rho. Yeah, okay. I have the TABC. And then plus some commutator. The problem is this one. This is called anomaly. Anomaly means that it's something like this. You have this will associate with these three currents, and then you have a triangle here. Now, if you naively do something, it looks like this term is not present. But this integral here is linearly divergent. If you just do the power counting. So the integral is not well defined. In order to define the integral properly, then you have to introduce certain regularization which cannot maintain all the identity you want to keep. You can only keep some of them, but not all of them. And the people who try to do is to keep the identity correct for the vector current, but not the actual vector current. And the reason is that people think the vector current, especially associated with isospin current, so this should be conserved. But actual current doesn't have that proper strong requirement. Okay? Then when you do that, then you get this divergence in this term. Now this gives you a trouble. Now let me just say D ABC is equal to 1 half trace TA TB TC. Okay. If this DABC is not 0, then you don't have the ordered identity, and this ordered identity is needed to show that the theory is renormalizable. Okay? So, what we have to do is to make sure when you construct a gauge theory for electron weak interactions, this must vanish. Okay, so that's the requirement. Now, it's very easy to show that for SU2 that's the case. So for pure SU2, then the P ABC is 0. And it's very easy to see because PA equal to 1/2 tau A, TB equal to 1/2 tau B, and TA, TB equal to 1/2 delta AB, right? The commutative, anti-commutative tau and tau, just a delta function, a canonical delta. And then we have B, A, B, C for SU2, just equal to 1/2 delta AB, and then I have a trace 1/2 tau C, and the tau is no trace, so this is identical to 0. So that's okay, but the electron weight is SU2 cos U1. And because of this, that this anomaly is not guaranteed to vanish. You can read the Chen and Lee. They give you a simple condition. So I will just refer to Chen and Lee. That the condition for D, A, B, C equals 0 is the following, that you sum of Q, it must be 0. And the Q I is the charge, fermion charges. Let's take one generation as an example. One generation. Then we have electrons, neutrino, we have up quark, we have down quark, right? So the charge for the electrons will be equal to -1, only from the electrons. For the quark, we have charge from up quark, 2/3, and then we have down quark is -1/3. So it's 1/3. And it looks like they don't add up to 0. But you remember, we have a color quantum number, so there are 3 colors for each of them. So we have to multiply this by 3. And that equal to 1. So -1 QL plus QQ equal to -1 plus 1 equal to 0. This works for one generation, and then you can, it's obvious that for each generation this works. So for all 3 generations, they're up to 0. So that's another evidence why we need the 3 colors. Without the 3 colors, the anomaly will not cancel, and the theory will not be renormalizable. Okay? So that's the end of today's lecture. What I want to do next week, actually the next 2 weeks, is talk about neutrino masses. And the neutrino oscillations. Okay, I hope we have time for